Hello, my dear students. I welcome you once again to this current video lecture. In the last lecture, we studied the important point from the chapter that is called as what is meant by conductance or conductivity water, as well as we solve the two different numericals on the calculation of specific conductance and equivalent conductance. Now, in the current lecture, we are going to study the new point from the chapter that is called as the variation of specific conductance and equivalent conductance with respect to the concentration, or we can say that the variation of these specific and equivalent conductance with respect to the dilution. So we know that this specific conductance, what is by this specific conductance? This specific conductance is nothing but the conductance given by the number of ion pairs present in a given volume of the solution. It depends upon how many number of ion pairs are present in a given volume of a solution. So on that basis we can define this particular specific conductance. So as we increase the concentration, it is directly proportional to the LS, that is a specific conductance. Why this is so? Because as we increase the concentration, number of ion pairs going on increasing, and as this number of ion pairs increases, gradually it increase the value of this type of the specific conductance. Now whenever we consider the specific conductance, it depends upon the nature of the electrolyte, whether that electrolyte is a strong electrolyte or it is a weak electrolyte. So depending upon that, the value of this specific conductance get affected. What happens in the case of strong electrolyte? That electrolyte is already dissociated, or it has the maximum ionization or dissociation. So we can say that it shows the more value of this specific conductance. On the another hand, if we consider this weak electrolyte, it get partially dissociated, so it shows the lower value of this specific conductance. Now as we increase the concentration, then what happens in case of this type of the second conductance, that is a this lambda, that is equivalent conductance. So again this equivalent conductance get altered with respect to the particular concentration of an electrolytic solution. Now as far as this lambda, that is a equivalent conductance, is considered, so if we want to study the effect of this dilution, if we want to study the effect of dilution on lambda and ELS, that is a on equivalent conductance as well as on this type of the specific conductance. So what happens, we know very well the equation for calculation of this particular the lambda, that is a lambda is equal to LS into 1000 divided by C. So this is the equation for the calculation of equivalent conductance. So if we look toward this equation, we can say that as this concentration and this equivalent conductors lambda, they are inversely proportional to each other. This lambda and C is inversely proportional to each other. So now if we consider the relationship between this lambda to that of the dilution, so what happens when we plot a graph of this equivalent conductance with that of the volume, that is a dilution, then what happens, gradually this equivalent conductance going on increasing, this value gradually going on increasing. So what happens, if we increase the dilution, means what, if we increase the dilution, it means at the same time we decrease the concentration, means we increase the dilution, at the same time we decrease the concentration. But what we can say here, as this concentration going on decreasing, it alters the, or it changes the value of this equivalent conductance, means as this concentration decreases, this lambda going on increasing. But if we consider this LS, what happens, this LS is, we know that this LS changes with that of the concentration of a particular electrolytic solution. As concentration increases, it also going on increasing. But what happens in this case, if we increase the dilution, what happens, the value of this ls decreases. If we increase the dilution, the value of this ls decreases. So we can say that as this value of ls decreases, naturally this lambda may be going on decreasing, but this is not found here. What happens, no doubt this ls decreases with dilution, but at the same time the factor 1 upon c, the factor 1 upon c increases. The factor 1 upon c increases in this equation, and that's why overall, if we consider the overall effect, no doubt ls going on decreasing with the dilution, but at the same time this factor 1 by c going on increasing, and due to which we can say that whenever a plot of lambda versus dilution is there, that value gradually going on increasing, and at a certain point we get a fairly constant value of this particular lambda. So the difference between this value, or that last value of this equivalent conductance, is called as the lambda 0 value. So this is a graphical representation for dependence of lambda on the dilution. Now if we study this graph for the dependence of lambda on dilution, so for this purpose we take that some examples of the equivalent conductance at 25 degrees centigrade for various types of the electrolytes. So in this table, different type of the concentrations are given, as well as different type of the electrolytes are given. Some are the strong electrolytes, some are called as the weak electrolytes. Now what happens here, we are going from fairly dilute solution to the concentrated solution. So first of all, if we consider 0.005 highly diluted solution, what happens in this case, if we consider the strong electrolyte as a HCl, it gives a very high value of equivalent conductance, around 422.74. Now if we increase the concentration, what happens, we get here 0.001. So we get the value for this lambda is equal to 421. So as we go from lower concentration to the higher concentration, what happens, at the higher concentration we get the value of 392.32. So this is the case in terms of the increasing in a concentration. Or in another way we can say that if we go from 0.1 up to the 0.0005, that is a, we go from higher concentration to the lower concentration, then what happens, this value of equivalent conductance going on increasing from 392 to the 422. Okay, this is a case for this HCl. The same case is there for this KCl also. If we go from higher concentration to the lower concentration, means if we increase the dilution, what happens, it affects the value of this lambda, that is we go from 128 to the 147. And in the last case, if we consider this acetic acid, again in this case also we go from 5.20 to the 67.70 value of this lambda. So from this tabular form we get some idea regarding these different type of the electrolytes. So what happens from this table, we can say that in case of these strong electrolytes, like HCl and KCl, what happens in case of the strong electrolytes, this lambda does not increase, this lambda does not change appreciably, with dilution. Lambda does not change appreciably with dilution, because if we consider their initial value is a 392.32 and the final value is a 422.74. So we can say that there is no any drastic change can be occur in the highly concentrated solution to that of the lower or weakly concentrated solution. So we can say that in case of the strong electrolytes, lambda does not appreciably change with dilution, but we consider the weak electrolyte like acetic acid, we consider the weak electrolyte like acetic acid, it has lambda value change, lambda value change, lambda value change appreciably. In this case, lambda value change appreciably, because if we consider initial value of this acetic acid at a high concentrated solution is equal to 5.20, but at the highly diluted solution it will give us the 67.70. So this difference is a more in case of the weak electrolyte. So we can say that in case of the strong and weak electrolyte, this type of the different results can be obtained at 25 degrees centigrade for the value of equivalent conductance. So we can say that in a short, if we plot a graph of this equivalent conductance with a dilution, this equivalent conductance gradually going on increasing with increase in the dilution. At a certain point we get the fairly constant value of this lambda. So we can say that these results of the dependency of this lambda on dilution can be cleared with the help of this particular tabular data. In this case, strong electrolytes show the less effect of this type of the dilution because they are the strong electrolytes. They initially gives us the maximum ionization, so they gives us a high value of lambda, that is a 392. After the dilution also they gives a very small increase in this type of the results of this lambda. On the other hand, if you consider the weak electrolyte, they get partially dissociated at the concentrated solution. It gives the value of only 5.20 of lambda, but as we increase the dilution it gives the drastic change. So it gives the value of lambda at very dilute solution equal to 67.70. so this difference is a drastic as compared to the difference in a strong electrolytes. So this is a difference between the variation of this LS, that is a specific conductance, and equivalent conductance with concentration, or we can say that with dilution. So this is the first case of the particular variation of this specific and equivalent conductance. Now what we can say that from this particular study of lambda of this weak electrolyte, we can say that whenever we go from highly concentrated solution to the lower concentrated solution, what happens, the change in this value, the change in value is a we can say that it is a get drastically change. So this type of variation, this type of variation of lambda with respect to the concentration is given by one equation. This type of the change with respect to the concentration can be given with the help of one equation, that is lambda is equal to lambda 0 minus b into under root c. So by using this equation, this behavior of equivalent conductance can be given with respect to this temperature. In this case, this b is a constant. In this case, this b is called as the constant. This b is a constant. Now this equation, the above equation is in the form of y is equal to mx plus c, that is the equation of straight line. So if we plot a graph of, now if we plot a graph of this lambda, that is equivalent conductance versus this under root c for concentration, for both strong electrolytes as well as the weak electrolytes, we get the such a type of the nature. So what we can say, if we plot such a type of the graph, we get a nature for this strong electrolyte like KCl, we get such a type of the straight line, it a straight line is obtained. So this is a case for strong electrolyte. But on the other hand, if we consider the weak electrolyte like acetic acid, this shows the parallel nature, this shows the parallel nature with that of the y axis. So this is the difference between the value of this lambda for strong electrolyte as well as for this weak electrolytic solution. So we can say that the increase in this equivalent conductance value with that of the dilution is obey, or it show the good results for dilute solutions, for dilute solutions of the strong electrolytes, but not for those of the weak electrolytes. Means this is very clear that if we consider this point, there is a variation of LS and lambda with concentration or with dilution. So this can be studied only by the dilute solutions. by the dilute solutions of the strong electrolyte, but not the dilute solutions of the weak electrolytes, because in case of the weak electrolytes, this nature is exactly parallel to the particular y-axis. So in this current lecture, we consider the one important effect of the variation of this Ls and lambda with that of the concentration, how this Ls and lambda can be vary. So for this purpose, we consider that the specific conductance. So specific conductance is nothing but the conductance given by the number of ion pairs present in a given volume. Depending upon that, we can predict the value for the specific conductance. So as we go from lower concentration to the higher concentration, the value for the specific conductance going on increasing. This case, this study is a different as far as the type of electrolyte is concerned, whether it is a strong electrolyte or weak electrolyte. Now if we want to study the effect of this dilution on this wavelength, what happens? As we increase the dilution, gradually the value of this lambda going on increasing, and at a certain point it gives the fairly constant value of this lambda. So this can be studied with the help of equation of this lambda, that is lambda equal to Ls into 1000 divided by C. So we know that as we increase the dilution, no doubt the value for this Ls going on decreasing, but at the same time the factor 1 by C going on increasing, and that's how we can say that the overall result is that with the dilution this lambda value going on increasing. The study of this dependency can be well studied with the help of this type of the tabular data by considering the different concentrations for the different type of the electrolytes, and from this we can say that for strong electrolytes this lambda does not appreciably change with the dilution, while the weak electrolyte shows appreciably change in that of the equivalent conductivity value. Now if we want to study this variation of Ls and lambda, we have to consider the equation lambda equal to lambda 0 minus b under root c. So this is a equation of straight line. So if we plot a graph of this lambda versus under root c, for strong and weak electrolytes we get the different nature. For strong electrolyte we get a straight line, while for this weak electrolyte we cannot get the straight line, but we get the parallel nature to that of the y-axis. So we can say that this type of the variation or this type of the study can be given well results with that of the very dilute solutions of the strong electrolyte, but not by the dilute solutions of the weak electrolytes. So we can say that this is a dependency of dilution and concentration with that of the Ls and lambda. So with this I stop here. The remaining point we will take in a next lecture. So thank you so much.